Now let's apply our problem-solving technique along with our solution for second-order undamped free vibrating systems to solve what seems to be a simple problem, but we're going to see that there is a good amount of nuance to it. So I have a problem statement here, and I've copied from the slides the problem-solving steps for finding our x of t. All right, so first let's put down some givens before we get into the actual steps we want to take here. So we have this hammer dropping out of the sky and hitting an anvil. So the anvil is initially at rest, the hammer is dropping onto it. They then connect with an inelastic collision, and then they're going to be stuck together, and then the system is going to oscillate because the anvil is initially on these 4 springs. So we want to find what happens after the collision to this system as they oscillate on the springs. So we're given some information here. So let's see. The sledgehammer strikes the anvil. So right before the hammer hits the anvil, it is going to have a velocity of 15 meters per second. The mass of the hammer is 6 kilograms, and the mass of the anvil is 40. Each spring, it's sitting on 4, and each of them has a spring constant of 1800 newtons per meter. So we want to find the motion of this system after collision, and I'm going to say that the position of the system is going to be x of t, and I'll illustrate that as we go through our model. All right, so now we can start on our problem-solving steps. So we can start on the modeling step. Basically, the modeling step is going to be how are we representing our system and what are we going to use in order to get our equation of motion. So we might need Lagrange's equations. In this case, we don't, because the system is pretty much simple enough that we don't need to do this energy method. We're going to be able to figure out what is the equivalent mass, spring, constant, and in this case, no damping, without using Lagrange's equations. So what we're trying to do is reduce this to a simple system that looks like this. So we have some equivalent mass that we're going to need to find that's on some equivalent spring. In this case, there's no damper on it. And we have 1 degree of freedom we're trying to track. That's going to be the x of t. Now here, I'm going to define x of t as positive down. It didn't tell me what to use as positive up or positive down. I'm going to proceed with positive down, and I'm going to just make sure I'm using that consistently. So we're going to find, we don't necessarily know up front, but we're going to find it is just a single degree of freedom, and we will find then the equivalent mass, equivalent spring constant, and this is an undamped system. So this is what that simplified system will look like. So before we get to the equation of motion, we need to figure out what is that equivalent mass, what is that equivalent spring constant. Now, this is where the modeling step can get tricky, is we have to decide what even is our system that we're representing here. So there's different snapshots in time we can think about in this problem. So there's the time when the hammer is still falling through the sky and the anvil is sitting there. And then there's the time where the hammer and anvil connect and they're instantly stuck together there. And then that system, because it's on springs, is going to oscillate. So what we need to determine is 1, what is our system we're representing, and 2, what is the time when time equals 0 when we start our timer. Now we don't want to start the timer in this case before the hammer impacts the anvil, because that problem, that scenario is not vibration. It's not oscillating. The anvil is stationary. The hammer is just in free fall. That's not what we're looking at in vibrations. The point of time we are interested in is when the hammer and anvil connect, because at that time, now our system is going to exhibit this oscillatory behavior. It's going to be vibrating, it's going to be oscillating on the spring system. So that's actually the situation we want to model, is the moment the hammer and anvil connect, and we're going to call that time 0. So we actually are going to start with this kind of more complicated representation that is then going to simplify down to our simpler one. So initially, we can represent the system this way, that at the moment they connect, this is going to be the mass of the anvil, this is going to be the mass of the hammer. They are stuck together, so they share 1 degree of freedom. We can still call it x, and it's setting on 4 springs in parallel, so each one with a value of k. But again, where do we want to get to? The simple spring mass damper system, or in this case, spring mass system that we have on the right. So how do we go from what we have on the left, which is a bigger representation of it, to the equivalent or simplified version of it? Well, so this one is, once we kind of realize what the system actually is we're analyzing, this particular one is not too difficult. So the equivalent mass of our system in the simplified side is going to be, I guess I'll write it on the same order here. So on the right-hand side, our MEQ, which will eventually I'll just call M. Well, the hammer and the hammer and the anvil each have their own mass, and when they stick together, that object is just going to have the mass of the 2 of them together. So that's going to be, we were provided that in the given, 6 kilograms plus 40 kilograms. So 40 kilograms will be the equivalent mass when the system is stuck together. That's 46, the 6 plus the 40. That is our equivalent mass. It's the mass of the hammer and anvil as 1 unit. Now, the equivalent spring constant. We have in our picture that the anvil is resting on these 4 springs, and those springs are in parallel. And each spring has a stiffness of 1800. So what we know is that springs that are in parallel, that is, that they all deflect the exact same amount, those we can just add their spring constants together. So if I take k plus k plus k plus k, that's 4 times k. Now I will reuse k later in this problem. Once we're past the modeling step, the m and the k I'm going to be using are the equivalent values. I'm just not going to be writing the EQ. So this k here is the 1800 that was given to be the individual spring constants. So multiplying them together, that means our equivalent spring constant is 7,200 newtons per meter. Right? Again, this 7,200 is what here on out I'm going to call my K or my KEQ. So this is now what the K is, and this is what I'm going to be using from M here on out. Right, so this is the modeling step. I have the KEQ and the MEQ, and again here there's no damping, so there's no equivalent damping coefficient. So now I can assemble my equation of motion. Again, a lot of times this will come out of using Lagrange's equations. In this case, I don't need to because I was able to find my MEQ and KEQ through other means. And through the simplified model, I just have this spring damper, the spring mass system here. So it's going to have the form of mx double dot plus kx equals 0. Right, so there is no external forcing after I start the timer at 0. There's no outside force acting on the system. There's no damping in the system. Again, this m and k are the equivalent m and k's from the modeling step. So that means that the equation of motion for this system is going to be 46x double dot plus 7,200 x equals 0. Right? Once I can get to this abstract step of just the spring mass representation, this is going to be what the equation of motion looks like. Right? So 46x double dot plus 7,200x equals 0. I'm using all base units here, so I'm not writing down explicitly the kilograms and the newtons per meter because I'm in base units, but probably I would want to attach some units with it otherwise. Right? So this one, getting the equation of motion once we have those equivalent values, is pretty straightforward. Now the identify step. So this is going to be really important, especially as we build more tools and more types of scenarios that we are able to work with. Now, right now, we only know one type of problem and how to solve it, but we need to look at our equation of motion and identify and make sure that we know what the solution is going to look like for this problem. So based on the equation of motion above, we know that x is our only time-dependent variable, so it's 1 degree of freedom. We have an x double dot and an x, but there's no x dot, so it's undamped because it lacks that x dot term. The right-hand side is 0, so it is free or autonomous. There is no forcing. So based on these characteristics of it, we can look in our tool chest at what the solution to a problem of this form looks like, and this is what we just covered in the previous two subsections here. We know that the x of t for a system that looks like this will be in the form of this a cosine omega nt minus phi. So that's what the solution looks like. We just have to kind of fill in the details here. So in this specific case, we're going to need to calculate the a, the phi, and the omega n so that we can get our total solution. And remember, in this case, the t, we're starting the timer the moment the hammer and the anvil are connected. Now, we know what the solution should look like, so going to our list of steps here, now we can find parameters. So in this type of system, we really only have one parameter, and that is the omega n. Well, really the a and the phi are going to come into play once we identify our initial conditions here. But let's start with omega n. Again, any 1 degree of freedom system, we are going to be interested in finding the natural frequency. So it's the square root of k over m, where k and m are the equivalent spring constant, equivalent mass. So I will use the 7,200 over 46. And if I do that calculation, I'm going to get a natural frequency of 12.51 radians per second. And the other parameters I'm going to need is the a, but again, that will depend on my x naught, which I'll determine in a second, and my x dot naught. The a, as we saw before, is going to be calculated using x naught squared plus quantity x naught dot over omega n squared. And we know how to find the phi as well once we have our initial conditions sorted out. So that's going to be the 4-quadrant arctangent of the x dot naught over our x naught omega n. So we'll have to come back once we do our initial conditions to figure out a and phi. So next step, identifying our initial conditions. What is our initial position? What is our initial velocity? Now going back up to here, to our problem statement, the initial position at least seems like it would be very simple. The anvil is at rest, it's on these springs, so we would naively say, well, the initial position of our system is 0. But remember, we're going to be measuring our initial position from the equilibrium position. Well, to start, before the hammer strikes, the anvil and spring are in equilibrium, it's at rest. However, we are measuring equilibrium from where the system is at rest, would be at rest. So that is the system at time equals 0. And we're going to see that actually the system does not start at 0, but actually it's going to be a little bit easier if we start with the velocity first. So we'll come back to the initial position. Let's look at the initial velocity. Before the timer starts, the hammer and the anvil are separate, and then they connect the instant the timer starts at 0. So the anvil is at rest before time is 0. The hammer is right before it strikes the anvil, traveling at that 15 meters per second, and then they are stuck together. So since they are stuck together and it's a perfectly inelastic collision, we can figure out the velocity of the hammer-anvil system right when the time begins by applying a perfectly inelastic collision between the hammer and the anvil. So this is how we're going to find our velocity, our initial velocity first. So what we know about a perfectly inelastic collision is that momentum is going to be conserved in an inelastic, perfectly inelastic collision. So the momentum right before it strikes is going to be the velocity of the hammer times the mass of the hammer, plus the velocity of the anvil times the mass of the anvil. And that's going to equal our initial, what I'll call the initial velocity, because from when the timer is, that will be initial, times our equivalent mass. Right? So again, total momentum before the strike on the left-hand side, total momentum of this after the strike on the right-hand side. So the hammer is traveling at 15 meters per second right before the strike, and the mass is 6 kilograms, plus the velocity of the anvil. Well, right before the strike, the anvil is at rest. It has no velocity. So this whole thing is going to just be 0. Equals then the velocity of the system after the collision times, well, we already know that after the collision and they're stuck together, it has a total mass of 46 kilograms. So the only thing we don't know from this equation is the initial velocity of that hammer-anvil system. So if we do that calculation, we get 2 meters per second. And it will be traveling down, so that is indeed positive. We want to be careful of the sign here, because again, from the model, I assigned that x was positive down. So when they collide, the anvil and hammer system will also be traveling down, so this is a positive value. And then this is the x dot naught. They're going to be the same thing. Now we can look at our initial position, and this is going to be just a little bit trickier to think about here. What is it initially? So again, naively, we would say, well, the anvil's at rest to start. It's just sitting on those springs, and then the timer starts, so it should be starting with an x naught of 0. It should be starting at its equilibrium position. But that is not the case, because the mass changes instantaneously when that collision occurs. So our system is, let's say it's up here initially, because the anvil was at rest. But what happens after they are combined is that the new equilibrium position should actually be lower, because it should compress that spring more. So the equilibrium position should be down here when that mass increases. However, it is actually up here initially. Right, so now I'll put that mass on. So right when they collide, now our system has a mass of 46 kilograms, not 40 anymore. It's actually above where it wants to be. There's this delta between them. So again, it's not intuitive, but initially, right when they strike, the system is at the old equilibrium position, where the mass on top of those springs was only 40 kilograms. But the moment they combine, the new equilibrium position is lower by an amount delta that we're going to find, because the new mass of our system is 46 kilograms. So actually, right at the moment of collision, we are going to find we are above the new equilibrium position that our system wants to be in. Right? So what we can look at here is the change in that force is going to be equal to the k times the change in position, or I guess I can just use delta since I'm already using it here. Right? So again, it was 40 kilograms, it's now 46 kilograms, so the change in force is going to be 6 kilograms times 9.81 meters per second equals 7,200 delta. So solving this, our delta is going to be 0.00817 meters. And again, this is saying that initially our system is 0.00817 meters above where the actual equilibrium position for this system, where the mass is 46 kilograms, should be. So this is actually above where it wants to be. So our x naught is actually a negative 0.00817 meters. So again, we want to think about this for a second. Our initial position is not 0 because at the moment of impact, the moment that they combine, our system's equilibrium point actually goes lower because now the mass has increased. So the physical position hasn't changed instantaneously. However, the equilibrium point has. So that's where this delta is coming from, where it's currently resting right at that collision point to where the new equilibrium point should be. So we get an x naught value that is negative here. All right, we have our initial conditions solved for, our x dot naught and our x naught. So now we can actually come back up here and plug those in to find our parameters. So if we plug in the values of x naught and x dot, we find that our a, well, that's always going to be positive, is 0.157 meters. Again, I want to be operating all in base units here to make life easier. And I'm going to find that my phi value is 1.62 radians. Right, so I do want to make sure that I'm using that 4-quadrant arctangent, and we'll look at this in MATLAB just to make sure it's doing it correctly. My x dot did come out positive based on my coordinate system, and my x naught came out negative. So what we should have here is a positive numerator. Our y value is positive, but our x value, the denominator, is negative. So positive on top, negative on the bottom. So positive y, negative x, this should be a quadrant 2 value. And we see that 1.62 radians is going to be in that second quadrant. Right, so we have our parameters. We'll double check them in MATLAB that came from our initial conditions. So now we can assemble our solution. Again, from the identify step, now we know how to put all of those pieces together to get our x of t. So finally, we can assemble. So our full solution here is that the position, the moment we start that timer, which is the moment that the anvil and the hammer are connected to each other, is going to be a, so 0.157, times the cosine of our natural frequency, which we found earlier was 12.51 times t, minus phi. And that is going to be in meters. Okay, so that is our full solution. That is the position once the timer starts from time 0 to infinity. That is the position of our hammer anvil system. And again, from how I initially made my model, I said that x was positive down. So when this value is positive, it's below its equilibrium point. When this value is negative, it's above the equilibrium point. Again, I will point out this x of t in this picture is being measured from the equilibrium point of our system, which again, thinking about the initial conditions part, that equilibrium point is below the initial position once the system is combined. But x of t, all of our degrees of freedom are always measured from equilibrium. So that is why it's negative initially. It's initially above its equilibrium point. So let's jump into the MATLAB code because we want to see how does this system actually behave once we run this equation that we found, and we just want to double check some of these values that we had before. So in MATLAB, I've put in some of the system parameters. So the masses of our falling mass and of the anvil, the equivalent spring constant, the equivalent mass, and finding all of these intermediate values here. So if I go down in here, again, just double checking, yes, the natural frequency is that 12.51, and how we're finding our initial positions and our initial velocities, just like we did before, doing it by hand. And we get the a value and the phi value that we are interested in. So if I print out a, get that 0.156, or I wrote down 0.157. I only took 3 significant figures when I wrote it, but same idea. And then the phi in radians, 1.62 radians. Again, that is in quadrant 2. So notice on line 20, I am using a tan 2 in MATLAB, and just so that we can remember what it's expecting with a tan 2, the order that we want to put, it's going to be the y or the numerator, comma, the value of the denominator or the x value there. So that's why I'm using the initial velocity, comma, and then the product of my initial position and my natural frequency. So I don't want to do the division here, or it's not going to do the 4-quadrant arctangent for me. All right, so in 22, this is where I am defining my function. So this is coming from that identify step and the assembly step, now that I know my A, my phi, and my natural frequency. So now I have x, and I made it here as an inline function just so I can use it a little bit easier in the next step. So I am going to simulate this for 2 periods. Notice above I define a period as 2 pi over omega n. A period of oscillation is going to be defined for free vibrations by its natural frequency. So this is going to have a period of about 1/2 of a second. So in my plot, I can make this longer. We can see what happens. I'm going to simulate this over 2 periods. So we're going to see 2 peaks in this solution. And then I'm going to plot it. So my time versus my x of t. I'm going to make a lot of points on my time. So that's why I'm using a lin space here. So let me just run this whole section. Okay, so it's running for these 2 periods. So we see 2 peaks slash 2 valleys here. And I'll make this bigger so we can really see what's happening. And I'm going to use the data cursor to make sure it's behaving the way we think it is. Now remember, it's graphically kind of the opposite of what's happening physically. I defined as x positive down. So let's see what happens at time 0 first, just to make sure this is acting correctly. So here at time is 0, the x value is negative, this 0.00817. And we'll see that this does indeed match what we had while doing this by hand for our x naught, at 0.00817 up, which is what we defined as negative. So yes, our initial position is correct here. We're negative, we're above that equilibrium point. Then we have that positive velocity, so we're going to see that the whole system is now traveling in the positive x direction. It's going to reach its lowest point, which is the highest value of x, and we see that that will be equal to the amplitude. I can't get there quite exactly, but we get really close to the value of a here, which we get the y value 0.1566, so that's really, really close to the value of a that we had before. And then it's going to oscillate. There's no damping in this system, so the oscillations will never get smaller. So now it goes back above the equilibrium point, and it goes to its highest value, or its highest vertical value, of negative a, so negative 0.1566. And then it's just going to keep going from there. So because there's no damping, this just keeps repeating forever. But we see the highlights here are that the initial position does agree with what we had with our hand calculations, and better. We designed it that way. And we see that it has a maximum of a minimum of negative a, and it just keeps oscillating. So in the end, we have our graphical representation of our plot. It agrees with our initial position, at least. We can see that immediately. It has a slope that's positive, so that agrees at least by sign with our x dot naught. And again, really what we were going after in this problem was our value of x of t, and we found through all of the procedures, all the steps in the procedure, the modeling, the equation of motion, our identify step, parameters, our initial conditions, and then finally assembling it, that we have a closed form solution for the position of this system once the timer begins. Again, we've defined our system as the Anvil hammer system, and the timer is beginning the moment they impact, the moment that they stick together.